value. And Wade. Wade, I didn't see Wade. Yinglin's not here yet. She always comes late. Yuna. Yes, Yuna. And Zibin is here. And Frederick. Oh, and Wade. Okay. I think we're about ready. I saw Yao Yang, but I didn't see him now. Why not? Okay, first things first. Let's, Tuesday I handed out the wrong sheet. We're going to do a little here. I want you to do number 1. I want you to try number 1. Number 2, this is integration by parts. I'll talk about it. Would you do me a favor? Could you pass these out? Okay, I'm just going to remind you, we have this formula that says the integral of fg prime, I'm just writing it very sketchy here, is equal to fg minus the integral of f prime g. That's the integration by parts formula. And I want you to try number 1, number 2, and then for those of you who are very fast, thank you. I'd like if you're real speedy and you get 1 and 2 done, try 6. 6 is really hard. Or I think it's really hard. But give that a try. We're going to spend a few minutes on this just because I think the more you practice these and the more you see them, the better you get at them. Thank you. Thank you very much. Does everyone have one of these? Integration by parts? Okay, good. Take a few minutes. We'll take a look at them. For those of you who pay a lot of attention to the schedule I put up online, you should know that I changed it a little. And the next quiz was put a day off further down the line. So in case you're try to be aware of those things. Why don't I even tell you what day it is? That would only be fair, wouldn't it? Schedule. So So Zimin, Yuna, Xiahao, Park, Kim, Xiahao Chen are not here. Okay. Let's see. Today is the 18th. Oh, okay, so the next quiz will be in a week. So that'll be the 25th. I think that's the 25th. It's a Tuesday. No, it's a Thursday. So,
I mean, February, right?
No March. That's the end of
February, yeah. I can't wait.
Spring break.
Thanks. Spring break. It's around when our final is. We're working on 1, 2, and 6. And if you get 1, 2, and 6 done, you can go on to anything else. And, yeah. Up through 7.4, which is what we're going to do today.
from 7.1.
Everything up till 7.4 that we've done.
Everything?
I mean, it will, probably emphasize what we've done since the midterm.
So it will also cover 6.5. Not sure.
The past is all present. Anything we've done in the class from the first day could be. Probably won't, but I say that because when we get to the final, it could be anything, right?
Yeah. And maybe, just maybe something from 7.5, maybe, but only if, see, it depends on how things go on Tuesday. Okay.
Well, good, because we're only going to spend a few minutes on these. This is more Tuesday's lesson. All right. I hope everyone's had a chance to at least try 1 and 2. I want to say something general about this technique. Again, it's somewhat, it requires a little creativity and a little thinking. You can't just jump at it. And the reason is, we're starting with the idea that there's some kind of product here, and we want to break that product up into 2 functions. And one of those functions, we're going to find its antiderivative. Another, we're going to find its derivative and try and integrate that product. This other stuff here isn't a problem, right? It may look ugly, but it's just there. We don't have to integrate it. So the key is to guess right, or to break this up in such a way that this is simpler. Now, in some cases, like number 1, it's not even obvious that there is a product here. Right? What are the factors? Well, when there's only one term here, you always have the possibility that 1 is a factor, right? And so the right guess in this case turns out to be f as the log of x plus 1, and g prime as 1. So when we go through this process, f prime becomes 1 over x plus 1 times the derivative of x plus 1, which is just 1. And g becomes x. And so this turns our integration into, again, going down the diagonal, find out this term, x log of x plus 1, minus the integral of what's on the bottom here, which is x over x plus 1. Now, this should be fairly straightforward. But it may not. This is kind of a little, if you haven't seen this before, it's a little tricky, but the obvious thing to do is to make this integral of x plus 1 minus 1 over x plus 1. The x plus 1 over x plus 1 is just 1. And then we have to just subtract 1 over x plus 1. And so we get x minus the log of x plus 1 plus c. And then we subtract that from f times g, which is x log x plus 1. I'm not going to write out the whole answer, just as long as you see the process. Okay, would someone like to suggest, well, for number 2, x e to the integral of x e minus x. Okay, so sure, there's a number of possibilities here. The product could be x times e to the minus x. It could be x e to the minus x times 1. And then either of these we could make the f or the g. But I think there's an obvious choice. Someone want to suggest an obvious way to break this down? F equals x, and g prime equals e to the minus x. Now, if that isn't obvious to you, think about what's going to happen next. we're going to find the derivative of this, which is going to be 1. That's pretty simple. We're going to find the antiderivative of this, which is going to look a lot like e to the minus x. And that's what we're going to have to integrate. 1 times whatever the antiderivative of this is. Which again, we'll do it. It's e to the minus e to the minus x. So this just becomes, I hope by now you're getting my strategy here. Always you look down the diagonal, minus x e to the minus x minus integral, what's on the bottom, minus e to the minus x. 2 minuses are a plus, so this just becomes x e to the minus x plus the integral of e to the minus x, which is e to the minus x plus c. So again, that's a really simple one. Now, I want to show you number 6 for a real specific reason. There's a good chance I will mess it up in the middle because I'm up here on the board and it's tricky, but you know, a little luck I'll be able to pull through. Number 6 is just an example of a problem where you look at it and you sort of know, well, it happens to be a definite integral, which itself is not a problem. X log x squared dx. You kind of know that this has to be a integration by parts problem. If it's not, who could tell? Who could tell what it could be? I mean, okay. Did I see Una come in late too? Oh yeah, you're here. Okay. So we're just missing Kim and Parth and Shia. Oh. Wait a minute. You're Gia. Gia. Okay. But again, you know, now there's really 4 factors in here. So it's not at all clear where we're even going to start. And as it turns out, having spent quite some time yesterday working this over, I found that there are 2 different ways you can do it that both work. They just kind of run around in a different way. The way I'm gonna show it, I said f equal to x log squared of x and g prime equals x. But if you want to have some fun, you could try this with f equals log squared x, g prime equals x squared. I don't know, they're both about the same difficulty. This is weird for a few reasons. One of them is when we find the derivative of this, it doesn't look particularly simple. However, because there's a log of x in here, we're going to get a 1 over x, which is going to cancel what happens over here, which we're gaining an x above the numerator. So, all right, let's give this a try. F prime of x, f prime of f of x is what? Well, we have to use the product rule here. So x times the derivative of log squared of x. That's 2 times the log of x times the derivative of log of x is the chain rule over x plus log squared of x times the derivative of x, which is 1. That doesn't really look simpler, does it? But life doesn't always work that way. G, of course, is x squared over 2. Probably going to need another Okay, so what is this equal to? It's going to be equal to x cubed over 2 log squared x. That's this term and this term. Minus the integral of the product of these two. Let's just eliminate that right away. Oh, and when we multiply this times this, the 2's cancel. So we have x squared log of x plus x squared log squared of x dx.
2.
Over 2? Okay. Said, All right, now why is this any simpler than the original problem? Well, we ended up with log squared, x squared log squared of x over 2 here, right? And it's still over here. Gee, I really need a lot. I need some kind of expanding board. Well, what I'm going to do, let's first propagate this through. This is minus this and minus this, right? So since this and this have the same function, it's just a factor here, I'm going to move this back to the other side. So I'm going to add x squared log squared x over 2 to the other side. Over here, giving me 3/2 x log squared x. No, log x squared. And that's still equal to x cubed over 2 log squared x minus x squared log of x. That took away the requirement to figure this out, which of course is my original problem anyway. I don't want to go into a loop where I never get to the end. Okay, so what can I do about this? Well, this looks like yet another integration by parts problem. So let's take that over here, do it separately. This clearly is simpler than the original problem because we don't have 2 logs. We don't have log squared, we just have log times x squared. What are we going to do with this now? Well, it again looks like we want to simplify the log by setting that equal to f and g prime equal x squared. So f prime is now 1 over x. G equals x cubed over 3. So now this becomes x cubed log of x over 3 minus the integral. Oh, now this is finally going to simplify x squared over 3. Or x cubed log of x over 3 minus x cubed over 9. All right, so that's what we're going to plug in here. Right? All right. X cubed over 2. I digress. When you're doing a problem like this at home, lots of paper. Lots of paper, so when you make a mistake, you just rip it up and throw it away, right? But, you know, you can write small, but you know, don't crowd yourself to the point where it gets in the way of getting the answer. Okay, so x cubed, now I'm getting sloppy, x cubed log of x over 3 minus x cubed over 9. That's almost the answer, except that's 3/2 of the answer. So we want to multiply by 2/3. So we'll get x log of x squared dx equals 2/3 this quantity. You can't simplify any of these terms, but you could multiply in all the constant factors. So might as well try that. 2/3, the 2 goes away, and this becomes a 3. This becomes 2/9. This becomes 2 over 27, and when you propagate the minus in, this becomes minus and this becomes plus. So I would never, ever do a problem like this, get an answer like this, and not check it. Let me check it and find the derivative. I'm not going to do that now, but you're welcome to give that a shot. Okay, that's all I'm going to say about integration by parts. Are there any questions? Yes.
For that part on the board,
This part?
does it matter if I switch F and G to value?
Okay, I'm not
If
sure.
I put
You mean if you made f x squared?
Yeah, does it matter?
Well, yeah, because let's just try that. So if we make fx squared and g prime log of x, the problem we get into here, okay, so f prime is 2x. Now what's g? What's the integral of log of x? We can do that, but it
We have a formula.
we have a formula, yeah, we could do that.
But once you have
Well, actually, let me back up for my statement. I said, no, don't do that. I'm suggesting you don't do that because, not because it won't work, it might work. We'd have to take a look. I mean, whatever it is, we then get a new integral x squared times that result. And that we might be going around in circles, we might be getting closer, we might not. I just think the way we did it, gets an answer in a more straightforward manner. As I said, well, I erased it, but my choice of putting x log squared x and x as the terms, it's not the only way you can do it. I found you can certainly do it by log squared x and this x squared. That will work too. You'll get to the same result, but through a different set of steps. So, okay, other questions about this? I would try not to put something on the quiz or the exam that's so tricky that you spend the whole, whatever hour, 2 hours you get, working on it to get it. But, there's homework, so you should practice, practice that. Again, there's one more interesting thing about this. I almost forgot. So, this is a definite integral, and it goes from 0 to 1. Now, what's the problem with the definite integral part of this? Someone see something that's problematic?
It can be 0. The x can be 0.
Oh, it's 3?
Oh,
no. The log of x
The log of x
cannot
be 0.
That's right. But yet, we can still do this, right? And we're gonna do this more rigorously, not real rigorously, but more rigorously in a later chapter called improper integrals. The trick is to see what happens. Let's just take a look at x cubed log of x, right? X cubed log of x. We want to evaluate it at 0. Well, x is 0, but what's log of x going to as you get very, very small? Goes to negative infinity. And we don't really know how to multiply 0 times negative infinity. We don't really know what we get, do we? However, I guess it would be good to have a graph. So, the graph of this, I don't know exactly what it looks like, but if you want to put this into your calculator, it's going to look something like this. That is, the factor of x going to 0 is going to overpower the log of x, trying to go off to infinity. And the proper way to evaluate this is to look at that limit. Let's try and find the limit as x approaches 0. Actually, I want to say x plus, I want to come from the right of this quantity. Now, does anyone remember how you would evaluate this limit? Any ideas? Does anyone remember L'Hopital's rule? Right. Well, in order to use L'Hopital's rule, though, we need a quotient, right? So what shall we make the quotient? I guess we could make it x cubed over 1 over. That might be the hard way to do it. How about we do it this way? Log of x over 1 over x cubed. All right, so we find the derivative on the top. That's 1 over x. The derivative on the bottom, that's going to be negative 3 over x to the 4th, right? And that becomes what? That becomes negative 1/3 x cubed. But what happens to negative 1/3 x cubed as x goes to 0? Goes to 0. Right? So it's a bit imprecise to plug in here. Well, let's do it. Okay, 3 times 1 cubed times the log of 1. Well, that's fine. That's 0. Right? Minus 2 times 1 times, that's 0 again. Plus, okay, here we have 2 over 27. Minus, now we're going to try and put in 0. Well, we just saw that this quantity, in spite of the fact that this is undefined at 0, this quantity goes to 0. The same with this quantity. And this is just very nicely 0. So this integral actually becomes 2 over 27. We will look at that problem more precisely, as I said, in a few days. All right. Any other questions? Integration by parts. Okay. Now take a deep breath as we switch over to yet another set of techniques. This isn't really a technique so much as strategy to solve a certain class of problems. So the first group I want to bring to your attention involve sines and cosines. And the most general way to look at this problem is integral of cosine to the n of x times sine to the m of x, where n and m are positive integers. Or 0, I mean, we can eliminate one of these. So let's start out with some basics. So we know the integral of the sine is the negative cosine. That's the constant. We know that the integral of the cosine is the sine plus the constant. All right, let's take the next step. We've seen this before. Sine squared x dx. We have to do a conversion here, right? Mm-hmm. Anyone recall what we convert this to? And I'm just going to remind everyone, because I think it's so important that rather than memorize things that, in a year or two, of course you won't remember, maybe in a month you won't, but if you know how to get there, it makes life much simpler. So the way you get there is you look at the formula for cosine 2x, which hopefully you have memorized. It's cosine squared x minus sine squared x, or if I plug in here, if I use the Pythagorean theorem here, right, what do I get? I get 2 cosine squared x minus 1. Or I can plug in over here and I'll get 1 minus 2 sine squared x. And that's where this sine squared is going to come from, right? If I solve for this, I'm going to get sine squared x equals 1 minus cosine 2x over 2. So that's what I'm going to do here, 1 minus cosine 2x over 2. And that's pretty straightforward. That's going to be x over 2 minus cosine minus sine of 2x over 4 plus c. And likewise, cosine squared x dx equals, it's going to be 1, well, we have to go back to this guy, right? So it's going to be 1 plus cosine 2x over 2. So again, x over 2 now plus sine 2x over 4 plus c. Okay, this is the basic building blocks we're going to use to solve this. All right, so let's first take a look at, well, the next step up. We're going to look at n equals 0 and n equals 3. Or, in other words, cosine cubed x dx. So what we're going to do here is we're going to break this up. We're going to break it up into cosine squared x times cosine of x. Then we're going to take this squared term and we're going to use the Pythagorean theorem on it. So we're going to get 1 minus sine squared x times cosine x And then, of course, we'll just distribute cosine x minus sine squared x cosine x x. Now, what has that done for us? We know how to integrate cosine of x. That's no problem. Here we have a perfect application of reverse power rule. We know this is going to be sine cubed of x over 3. Here's sine of x. As long as we have some, power, sine to some power plus 1 cosine, we can do this, right? Or we can reverse it. We can, if we have cosine to some large power times 1 sine, we can use this inverse power rule. Now, I just used 3, but if I were to use n, I would still take off 2 here, and I would have n minus 2. And what would happen? Well, here I would have n minus 2. Did I do that right? No. What I want to do? I don't want to go there yet. I'm sorry. Just leave that. No, I guess I can't. I guess I have to go through that. So let's do it. Does everyone see that the same idea works with sine to some odd power? Right? I can say sine cubed is just sine squared times sine. Sine squared is 1 minus cosine squared, and I get the same strategy. If this is some larger number, n, where n is odd, how would I show that n is odd? I would say 2p plus 1. Okay? So this becomes cosine 2p of x times cosine of x. Since this is even, let me get this right. I can multiply this. This is, if p is 1, then it's the problem we just did. If p is larger, then we have cosine squared x times cosine 2p minus 2 times cosine of x. And this now becomes 1 minus sine squared x times cosine 2p minus 2 times cosine of x. So now when we multiply through, we have cosine 2p minus 2, plus 1, so it's minus 1, times cosine 2p minus 1 times sine squared. Oh dear. I think I'm painting myself into a corner. This is minus, right? Well, this is an odd power, which, if it's 3, we're done. If it's larger, then we're going to repeat this over and over until this gets down to where I can deal with this. Over here, what do I do with this? Well, I've got an odd power of a cosine and an even power of a sine. So I can repeatedly use the Pythagorean theorem on this, and I'll end up with even powers of sine times an odd, a single power of cosine when I'm done, which again lets me use the power rule. I don't feel like I said that very clearly, but I will come back to it in an example. All right. Yes. Question?
Oh, I just want to move the ball to y a little bit, but you just changed it.
You want me to move the board?
Yeah.
This board I can't move. It's the back board.
Okay.
Oh. I know what you need. Either this, or you need to move your seat. Is that better?
Yeah, that's better.
Okay. All right, so that's how you handle when n or n is odd. Right? You can convert the even powers to cosines that are even. And it's that one odd power that lets you use that reverse power rule. So with some work, this takes care of everything except what? Except when you just have even powers, right? We know how to do an even power if it's alone, but what if we have, yes. Well, let's take again a simple example. What if we have sine squared x before we get to that, I want to just try this. Let's look at sine to the fourth of x, right? We can still use this strategy, right? This is equal to sine squared x squared, which we can convert to what? 1 minus cosine 2x over 2 squared. Multiplying this out, what happens? We get 1 minus 2 cosine 2x plus cosine squared 2x all over 4. And this part is easy. This part is easy. What are we going to do here? Well, we're just going to repeat what we did before, only now with cosine. Right? So this becomes 1 minus 2 cosine 2x is all over 4 plus, now this is cosine squared 2x, so it's going to be 1 plus cosine 4x over 2. No, over 2, because it's over this 4, right? So this is a kind of a divide and conquer strategy, right? We take something big and we get it down to size. All right, so that takes care of sines or cosines that are to an even power. We know what to do if it's the sine is an odd power or the cosine is an odd power. So the only thing we're really left with is what happens in this case. Right? So there's another trick here, which I want to go back over here to where I listed the cosine of 2x. And now I want to remind you about what the sine of 2x is. The sine of 2x is 2 sine x cosine x. So that means this is sine x cosine x 2 times it squared, but over 4, right? So this now becomes sine of 2x over 4 squared. But we already dealt with sine squared, right? Now sine squared of 2x, but okay, you have to do a substitution. That's it for sines and cosines, right? For any n or m on the sines and cosines, it might take a lot of work, it might take a lot of paper, but you just keep breaking it down that way. You either use the substitution here, sine 2x, or the substitution here to simplify sine squared or cosine squared. And then eventually you get to where, you know, if you're multiplying an odd power times an even, you can get that down to using the reverse power rule. There's a little bit more. This takes care of most of the problems we're going to look at. But there's a related issue, and I'm gonna describe it this way. Recall that secant squared equals 1 plus tangent squared of x. If you ever forget this, right, you're wondering where does this come from? If you just convert this back to sines and cosines, this just says 1 over cosine squared equals 1 plus sine squared over cosine squared. And if you put this over a common denominator, you'll have cosine squared plus sine squared is 1. You can see it. You can see that it's correct. Okay, so let's look at this somewhat more scary problem. Well, if this was just tangent times secant, what would you think? Well, no. Take that back. Let's just go through this here. So I've got an extra set of tangents here, right? I have a tangent square, right? So tangent squared x times tangent x times secant x. And now I'm going to use this fact to convert this. So what does tangent squared become? Secant squared minus 1 times tangent times secant. Okay, let's distribute here. So I have secant x, secant cubed x times tangent of x minus secant x tangent of x. Okay, so well, what's the derivative of the secant? Does anyone recall? Derivative of the secant. is the tangent. Right. So if this is the if this is the derivative of the secant, then I can use the inverse power rule here. Secant to the fourth x over 4, right? And what do I do here? Same thing, this just becomes secant squared over 2. So, the point is there's a similar strategy as with sines and cosines, where you divide up odd powers into, you take out the even powers and convert them. If you just give some random trig function, this may not work. But when you're dealing with secants and tangents, it can work in that manner. Okay, let's take a look at some problems. Well, all right. Let me just do one problem here. Integral of cosine to the fifth of x dx. So what would I want to do with this? Well, the obvious thing is to take this and break it up into cosine squared times cosine cubed, and then take the square portion and convert that to sines. Right? That then becomes cosine cubed x minus cosine cubed sine squared x. Right? We did this already, didn't we? We could repeat it, but this integral becomes sine x minus sine cubed x over 3. Okay. So now we want to work on this. Again, we want to take out a sine squared here, or a cosine squared. And what do we get? 1 minus sine squared times cosine squared x. And now when we distribute, what are we going to get? Cosine x sine squared x minus cosine x sine cubed x. But each of these succumbs to this power rule idea. Right? This becomes sine cubed x over 3. This becomes sine to the fourth x over 4. So if we plug this in here, we then get our result. All right, are there any questions about this right now? I'm going to give you guys a break for about 5 or 10 minutes, and then I have a worksheet that I want you to try some of these problems. Okay? Take a break. just lost somebody. Oh well. You're going to get some practice with these on the board too, so we can talk more about these problems on Tuesday. The next subject has to do with a very limited class of problems. You might find in the long run you're going to use the tables to find these, but let's say we have integral of the form a squared minus x squared. Before we cover this, let's use its simpler brother. For a problem like this, often we're going to again use the Pythagorean theorem, or the Pythagorean identity, to simplify this after we've done a specific substitution, right? Specifically, I'm going to say u equals, x equals sine of u. So dx will equal cosine u du. And plugging in, we see we have the square root of 1 minus sine squared u times cosine u du. And then now this is going to simplify real nicely, isn't it? This is going to be 1 minus sine squared is cosine squared. Square root of cosine squared is cosine. So this is just going to boil down to cosine squared u du, which we know we're going to convert to 1 plus cosine 2u over 2, which will become u plus sine u over 2 plus sine 2u over 4 plus c. But now, of course, we have to substitute back, right? So for u becomes inverse sine of x. And what do we do with sine of 2u? Well, sine of u is x.
Sine 2u, 2 times cosine u, sine u and cosine u.
Say again?
We can break down cosine 2u to the 2.
I don't think you need to do that. I think if x is sine of u, isn't... Oh, no, it's not. You're right. So this is sine u cosine u over 2. So, bringing that up over here, we've got inverse sine of x over 2 plus sine of u just becomes x. And then what does cosine of u become? Well, let's go back here to x equals sine of u. Let's square both sides. And let's subtract both sides from 1. Right? 1 minus x squared equals 1 minus cosine squared, which is sine squared u. And now if we find the square root, you can see that okay, I guess I said this wrong. Sine u becomes square root of 1 minus x squared. And cosine just becomes x. And we had a factor of 2. So, actually, a somewhat difficult integral, but again, there's a straightforward method. Now, if we want to add a little complication, let's change 1 to a squared. Note that this number can be anything now, right? It doesn't have to be a perfect square, right? If this were 5, then a is just the square root of 5, right? So now our substitution is a sine u. Our derivative here, a cosine u. This is all going to kind of come back to a minus x squared, right? Okay. I missed something important here. A squared. So this becomes a squared, and this becomes a. What happens here, we just have a squared again, a squared here, a squared here. I take that part back. Let's look at that a little carefully, a little more carefully. This a squared u. This is, this becomes x over a. I'm not going to do the details, because I'm just going to make a mistake. We'll just assign this as a extra homework problem, right? To redo my steps, only being careful about what happens to A, right? Okay, I'm almost done with this. I just want to point out that if instead of square root of a squared minus x squared, it was integral of a squared plus x squared, you would want to think of what? 1 plus tangent squared equals secant squared, or a squared plus a squared tangent squared equals a squared secant squared. So the substitution you'd want to do here is what? U equals a tangent of x. sorry, x tangent a tangent. And again, that will cause this to simplify, get rid of the square root. All right. I have a worksheet that has some of these problems on it, and we'll spend a little time doing that, just to get a feel for this. On the front side, there are trig integrals, and on the back, there are trig substitution. So. I'm seeing at least one puzzled face, so if someone has a question about that, please don't keep it to yourself. Yes, a week. Up to today. Sorry. I have a lot of trouble keeping you to your yin, right? As I said, they don't look anything alike. Yeah, get different glasses. Have to run out of these. Looking unhappy. Just dash one and 2 music only. We didn't get one? How many units? Over 4. Okay, has everyone had a chance to work on? Has everyone had a chance to work on 1 and 2? Anyone need another minute or two to? You don't have to have solved it, just you've had a chance to beat your head against it, right? I want to contrast these because you have to go about these two problems very differently because one is an even power and one is an odd power. You wouldn't think that would make that much difference, but it does. So in the case of sine to the 4th, you want to look at the fact that this is sine squared. And we have a way of converting sine squared to something simpler, right? This is 1 minus 1 minus, I have to go back to my little mnemonic here. Cosine squared is, cosine 2x is cosine squared x minus sine squared x. Okay? I have sine squared. So this is 4 1 minus 2 sine squared x. So this is 1 minus cosine 2x is 2 sine squared x, or 1 minus cosine 2x over 2 equals sine squared x. Sorry about that. That's the way I always do it when I can't remember. Cosine 2x over 2 squared, which now I multiply out. I get 1 minus 2 cosine over 2x plus cosine squared 2x over 4. This part and this part I can handle right away. But here I have the same problem again, except now it's not a sine squared, it's a cosine squared. So I want to know that my conversion for cosine squared x is 1 plus cosine 2x. So this becomes integral 1 minus 2 cosine 2x plus 1 plus, but now this is already 2x, so it becomes cosine 4x over 2, all over 4 dx. And now I can just go at each part of this, right? 1/4 is x over 4. Cosine 2x over 4 is just cosine 2x over 2. So that's minus sine 2x over 4 again. Okay, now I have 1/8. That's x over 8. Now I have cosine 4x over 8. So that's going to be sine 4x over 32. Okay. But again, the strategy here, since it's even, is to use this formula, right, to convert it. Here we're going to do something really different. Right? Here we're going to say, all right, let's keep one sine of x, right? Now we have sine to the 4th, right? Which is sine squared squared, which is 1 minus cosine squared squared. Now we're going to multiply this out, and we're going to get a totally different type of problem to deal with. Sine x, 1 minus 2 cosine squared x plus cosine to the 4th x. And when I multiply through, I just get 3 very simple sine x cosine squared x plus sine x cosine to the 4th x. And each of these I can do pretty simply here. This becomes negative cosine of x. This becomes what? We're going to have cosine cubed x over 3. But then there's a minus 2, so this becomes plus 2. And then this is just going to be minus cosine to the 5th over 5. So again, 2 different problems, very similar looking, strategy is totally different. Right? Okay, please continue. So I'm happy with the other side of the sheet.
Which one? Oh, no, he just like boiled it. That's where. And then you just distribute assignments to every turn.
Yes.
Society excellence one.
Ah, no. I think those are supposed to still be done. Oh, yeah.
When you see something
So you already know how to do that.
you know that it has to be form because, like, when you take the
First time?
right, you have to multiply by
Oh, you're reading ahead then. That's okay.
So this thing that popped up in the paper, please use the bracket.
I think what they want you to do with these.
Like, it turns into this.
Well, have you done 4?
Whenever you see something in the form,
That was the important one. No, I think you're right. I think this is, please stop. Please stop at number 4. Again, something snuck into my worksheet that I didn't intend. 5 and 7, we're gonna come upon those later. So don't worry about 5 and 7 right now. We haven't really talked about that. Well, okay, this is fine. This you can convert to sine, right? This is sine squared 2x over 2.
How come this one is cosine squared?
Okay, let's take a look. Take a look. Fourth cosine, sine squared, sine squared, unfortunately, that's wrong. If you're using inverse power, you're getting about now you can convert that to cosine 2x. This you can convert to.
Wait, why is it over 3?
Because
Cosine 2x squared. Or sine 2x squared.
I got it.
And then you have to do the same thing again. You have to convert to sine squared and cosine 4. And I could get the same.
Wait, what?
you're gonna solve this.
It's not there.
Sometimes I just think in my head that maybe I should have a plus
Oh, it has to be. Oh, okay. I wrote this wrong. So cosine has to be just sine straight line.
Yeah.
Okay. Okay. I got it. Okay. So let's just expand it. Right? That makes sense to expand it. What's our identity? Because we just say it's cosine squared times cosine. Or you can do cosine cubed times sine. Or,
Okay, so
Actually, I'm supposed to.
f of x to the n times f prime of x
it's a guessing game.
No, the practice is before you
is
figure out
f
what
of If you go the other way, you have the power. So, for example,
Sine goes up.
There's no identity.
Or actually, I wanted.
You gotta find that identity. Find it.
I didn't write down the root. Oh, yes, 2 sine x.
What is
The sine goes in.
n minus 1.
Pull it out. You can make the whole equation change whatever this bullshit is.
Integrate both sides.
Cosine square x. And then you can just use that and just get the wait. No, there's no algebra. So it's not a separate term.
Yeah.
This is impossible.
Right. And I'm going to do 2 things. I'm going to change n to n plus 1. Right?
Understand how this works. Stop showing me with this.
So now, integrating, finding the root, and I'm going to divide by both sides.
No, like, okay, just think about it. Like, okay,
F of x.
third, you want to find out.
That's x and the fourth.
Yeah, so you're just thinking, sine third x.
Equal.
Yeah.
Okay, you can't do this. I mean, simple. But if you have a sine x squared, then it becomes really simple. Because, okay, just think about it. Okay, let's just look at cosine or
What I just
what is the derivative?
No, I don't know. I took Calc A over the summer. I didn't learn anything.
And specifically, I have
Okay.
yeah,
I agree.
times, well, minus, right? So, the derivative of the cosine is sine, negative sine. So this is f of x to the fourth times f prime of x. And that just becomes f of x to the fifth.
So it's almost like a substitution.
Yeah, and so you see you have like
Okay. So it's like the inside function of the
yeah,
No, now I understand what you're saying. See, I didn't understand. I was like, how is this even at all? Like, no, I got it.
yeah. No, see the chain rules.
No, I understand now.
Well, we have this.
Maybe you should take in one ball or something.
I mean, if you replace x with f of x and use a chain rule, I mean, you get that.
I'm going to read.
No, I'm planning on taking 2A and 2B both. It's
Yeah,
I don't have
but, you know, that's, you can apply that chain rule to anything, right? I mean, if I say,
I don't believe you.
derivative,
I don't even know why.
That's why you draw close box.
Yeah.
sine, notes cosine
Oh, that's true. That's true.
derivative of
But
x to
okay,
the fourth
is he like
minus
assuming
3x.
all like what's the highest? 4 or 5?
So,
like a bunch of like 4s, and you know that it's
I can make a rule like this. I can say f of x
And I was registered. She filled up by the time I checked. By the time I took the class, I was like, what? Within like 10 minutes, it was filled. I was like, yeah. I was like, whoa. And I was gonna take it because she was the only like constant score. She was like,
There's like this one professor, and then he has like I really used to but
you can make up formulas like this one.
yeah, well,
This one here.
for real, 12 p.m. 4 a.m. too, right?
Also, another way
like 5 classes, and I might even
Wait, actually, why would you do that too? I know, but aren't you?
I don't. How are you? Yeah. Wait. How are you doing? I don't understand how you're working. It's so little. How many classes?
4.
Oh.
So it's not like, and they're all major.
How many are you doing?
I find the derivative.
Yeah. So same like me. Except I don't know about that. Yeah.
Right? So, you know, I'm this way by integrating. This way by.
Well, I'd rather drop
Matter
it
what
out.
x is, we get cosine x to the n.
But why are you getting that?
Because and I don't every single class. I don't know. It's literally
As long as you know what
No, me too.
practice, there's homework too. Practice on homework, bring in questions, right? That's how we learn.
Alright, I'll have you know
Yes, but it's reduction formula.
meaning that was no actual
We could develop this ourselves, right? No, you don't need integration by parts. You need what we just did. Well, let's try it. Can you do it for your quiz? Okay. If you want to do it that way, don't make a mistake on the formula.
What's the WD?
Okay, so let's, I mean, I made a mistake.
Wait,
Let's,
Let's see how many.
let's try, so your reduction formula says sine to the fourth, right, I'm going to plug in, right, equals minus sine to the third. Oh, you want to do fine?
But how does that even help you? I will tell you, last quarter, this is you have to keep guessing. So you cannot.
But you had symbol, right? Wait, I'm.
Minus sine to the fourth.
Yeah, I put it by
I don't know.
he's really nice.
I wake up at 8.
Is he the night teacher?
No, he's at 10, and then the rest was conflicted by other classes.
Oh, I see.
And then I just think I had one more and I
If he's teaching anything,
But it's
Now, you have to say,
I mean, you know, I hear there's a very high drop rate at teachers. So maybe it was just me or like their
minus sine
But like, no, they're not. Every morning, I
classes are really good because you're actually interesting for me is that even if I do classes, I still see the same time.
I will ask my
It's kind of down. Late.
啊，我觉得
Yeah, I
这
see
些
that really
考
late.
过试的还是没有让别人在的，就从来不想。
Is that my fault?
I'd like to.
I finished.
加入。
我以前
After season 2 it sucks. No, I started season 2. Well, I started season 3 on video.
把他的腕儿就行了，但是就是要求要机器的这个，我也没有说，哎呀，说这严。
But I didn't have class on Monday.
散了。
Wait, so does that mean that it started on Sunday night? I guess it's yeah, no, anyway, keep on. And the third season was only taking only 11 hours of my time.
How long? Like almost an hour, right?
45
Crazy. Don't you ever get
Let's do a little work here.
I can't watch like one day.
I can cosine x.
I never find out whether or not they're successful. Like I have a huge problem with like Netflix shows and like Netflix shows, like they come out in an entire season somewhere, so like I'm really screwed for like that day. Exactly.
回去了，他给，哎呀，终于想。
So this looks a little like
有一回你们俩说吃什么？你俩那个我就知道，哎呀，带回去。
well, they have to be the same.
Anything?
有一次我们去他们家去，
How we convert one to the other,
但我知道
that's
也可能没法画，但我有。
That's what I'm waiting for. Because I haven't set up
let's yeah, just to see if we're on the same.
Or you, I think you can sub. I think you can sub. Not because one of them. That's a lot of facts. One of the facts.
I gotta say.
他对，他这个是以他的心里这么想的，觉得要想着，哎呀，我要是我的天，所以怕咱俩关系。
And what's this? 这大玩意儿，大玩意儿。往右玩，我开，然后就写。Could I get some about it? Oh, so
Right?
after 10
How that works?
yeah.
You buy it on my phone, you have it. Yeah, it's just like $5 a day.
往里头洗呀，等会儿我天。他那个包了。他那个包了10.3吨不是？哎，那个尼特美没跑。哦，对，他可能包了我们刚不问了吗？他说 cover cover the whole thing. Yeah. 这是好像也没讲，他讲了，但是他跟我没说。哦，不是，你是说这题吗？他就讲了2道。分数跟你一样。
Oh wait, no, I did it. Yeah, I did.
你学的不怎么好。这讲话怎么会这样子啦？上海的讲话是这样子。
我在上海那个读了3年高中。
So something wrong. So that's worth investigating where the error is.
我可以拉
我看他网上那个
Identical. But it is interesting how they're testing for some things.
我是看数学。
There's some error here. We'll find it. Wait. One of us. It'll probably be me. Okay. Are there any questions on number 4? Number 4.
现在还有老师的
Oh, yeah.
幸好不用，不然要我花200刀。
卖新的。对啊。
Number 4 is the integral of square root of 25 plus x squared dx. So what's the substitution I want to do here? X equals what?
$25 plus x squared.
No. I thought we learned that. But let's try it anyway. Let's see why this doesn't help us. Oh, you mean u equals x squared?
Yeah.
25. Okay, so du equals 2x dx.
Can be there.
So this becomes integral square root of u, but we don't have an x here. So that's why we've learned this technique. Right. So what do we want to try instead? What do we want to substitute here?
X to the 25 candidate square. 25 candidate square x.
Well, we want x squared equal to be 25 something. Candidate square, which is the same as saying x equals 5 tangent u. Oh, and so dx equals 5. Derivative of the tangent is secant squared u du. Okay, so this becomes square root 25 plus 25 tangent squared u, and dx becomes 5 secant squared u du. We can take the 25 out of here, right? And we have 1 plus tangent squared, which is secant squared. So now we have the secant, because it's the square root. Oh, we have another 5. So 25 secant cubed u du. Okay. What is the secant squared equal to? Let's see, 1 plus tangent squared u equals secant squared u. So we take out secant squared and make it into 1 plus tangent squared u times secant u. And let's distribute. So now we have to find the integral of the secant plus tangent squared u secant u. Okay, what's our next strategy here?
Substitute twice. Substitute twice.
No. This is, I mean, this we have somewhere, right?
Yeah, but
Right? So this is the problem. Right? So what's the derivative of the secant? What's the derivative of the secant? Secant is the cosine to the negative 1, right? So its derivative is cosine to the negative 2 times the sine, but with a negative sign, right? So derivative of the secant is negative secant squared. Wait a minute. No, it's negative secant times tangent, right? Never helps to put your notes away early.
because you can let the derivative of tan x equal to the secant square x.
Derivative of the tangent, okay.
Oh, sorry, this doesn't work.
Oh, no, I want to look at that too. Derivative of the tangent is the secant.
It doesn't work.
Secant squared? You sure? Wait a minute. So what's the derivative of tangent cubed? That would be 3 tangent squared times the derivative of the tangent, which is the secant squared. Oh, that's not going to help. All right, something for us to do on Thursday, right? I mean, you can